Alright, so we've discussed the formation of epoxides, and of course we know that an alkene plus MCPBA can give us an epoxide. And there are two faces of that alkene. As of right now, there is no difference between those faces, so we should get a pair of enantiomers in this reaction, and we should get a 50-50 ratio of these enantiomers because there's equal likelihood of the epoxide forming on either side of that alkene. But what if we want only one enantiomer? What if we want to favor just this one that I've underlined? In that case, we need to use a chiral catalyst to produce a chiral environment where that enantiomer is favored over the other. So essentially we want to favor one side of the alkene over the other. And in this case, of course, we'd want to favor the top face of the alkene coming in from in front of the screen rather than behind the screen. And that way we could get an unequal distribution of these enantiomers. Another way to think about this chiral environment is to think about your left hand and how it can tell the difference between the left and the right glove. Right? The left glove fits on your left hand perfectly. The right glove does not. And I'm sure you remember a time when you were a little kid, you put the right glove on your left hand by accident. It sort of fits on, but it feels kind of weird, and your hand doesn't work as well as it would with the left glove on it. Your hand is the chiral environment, and the two gloves are the two enantiomers, and your hand can distinguish between them and essentially make a chiral environment that can produce or distinguish between these two, and thus we can favor one of these enantiomers over the other. So how do we use a chiral catalyst? Well, this reaction works with allyl alcohols or allylic alcohols. And this was developed by K. Barry Sharpless, who won the Nobel Prize in 2001 for this chemistry. So we can take an allylic alcohol, and of course an allylic alcohol doesn't have to have this methyl group here, so let me erase that. Any alcohol that's on a CH2 that's next to an alkene is an allylic alcohol. What we're going to use then is titanium tetraisopropoxide, and we're going to use diethyl tartrate. Which will give us our chiral environment. So this is plus diethyl tartrate. And we could also use minus. And of course, minus has just the opposite stereochemistry at these two chirality centers. So we can use either the plus or the minus, and sometimes we abbreviate that DET, so it's a little easier to write out, a little easier to describe to people. So we mix our titanium tetraisopropoxide with either plus DET or minus DET, and some oxidizing agent that can provide the oxygen in our epoxide, and that's going to be set up like this. There's our allylic alcohol. Here's our oxidizing agent, T-butyl peroxide. Here's the titanium isopropoxide, and we're going to use plus DET in this case, and we're going to produce this version of the epoxide. That enantiomer. And this would be 2s, 3s, 2, 3 epoxy, 1 hexanol. And we get this in 99% EE, 98% EE, excuse me. Which means we have 99% of this enantiomer and 1% of the other enantiomer, which I'm not going to draw. So we get very high EE in this case. So how do we know that we got the 2s, 3s version? Well, that comes from running the reaction. And let me look at this little mnemonic here. So Dr. Sharpless developed this tool, which is a generic allyl alcohol. You might see it in the book as sort of a allyl alcohol with generic R groups in a box. And what he, when he studied this reaction, if he found out if he uses plus DET in that previous reaction I just showed you, we get addition above this box, this plane. If you pretend that this blue box is a plane. If we use minus DET, we get addition below. So remember we're adding the O for the epoxide, either above or below the alkene. And now we can predict that if we remember this device here, this plane with a generic allyl alcohol in it. So let's look at one more reaction. Let's take our same allyl alcohol. In this case, though, same oxidizing agent, same titanium. I'm going to use minus DET. And so what we want to do is line this alkene, or this allylic alcohol, align it so that it matches our box. So I'm going to redraw it right up here. And I'm going to put the alcohol in the same position as my mnemonic here in the blue box. Then I'm going to add the rest of my species, which I believe is a 3-carbon chain trans to the OH. So now I have my 6-carbon alcohol. It's got the alkene in it, and I'm using minus DET. So I predict that the epoxide will form below this alkene. So below this alkene, I would get something that looks like this. And then if I wanted to translate that back to my blue drawing, and keep everything in the same orientation as my original molecule, I hope you recognize that I would need to just rotate this one around, the line in the plane of the screen. And so I would need to draw, actually, the epoxide above, in this case. And that would be the desired product here. This would be 98% EE, exactly the same as what we found with the plus DET, but with the other enantiomer. And so now we can see, in this case, this is one brief example of how we can favor the outcome towards one enantiomer versus the other. This is where a calculation of percent EE is very useful in order for instance, Dr. Sharpless to determine how effective his mnemonic is and his enantioselective epoxidation is.